Okay, here's our day 8, some free response scoring guides for a couple of problems about polar areas. I've done some adjusting, especially on the second problem, so hopefully this is focused better than the last video, so you can see that pretty well here. We're given the graphs of two different polar curves. R equals 3, and that's simply a circle with a radius of 3 centered at the origin there. And then that other one, R equals 4 minus 2 sine theta. And we're given the two intersection points of the curves. And this is why I changed the assignment in section 10.4, because the book was wanting you to find a lot of these intersection points by hand, and the AP exam does not typically want you to do that unless it's something very, very basic, which we'll see on the next one. So they tell you in this problem that pi over 6 and 5 pi over 6 are the intersection points, and I've kind of marked that on our graph there so that we can see that this region that we're trying to find the area of in part A is really made up of two parts, and the first part of that is just this part that's kind of above this V shape here. It's the part that's below the curve of 4 minus 2 sine theta, just between pi over 6 and 5 pi over 6. And so to find the area of that region, we're just going to do our 1/2 r squared theta, or r squared d theta, sorry, and integrate that. And that's what you see here in the scoring guide. 1/2 integral of, here's r squared d theta, plugging that in for r, on the bounds from pi over 6 to 5 pi over 6. You don't actually go from 0 to pi here, because like if you're looking at this little piece here, that's not below just this curve. It's actually inside the circle instead. But if we just look at the piece from pi over 6 to 5 pi over 6, it's only this equation that we're interested in. So we can find that area using calculus, 1/2 the integral of r squared d theta. The rest of this shape, all of this, is actually just part of a circle. It's not an entire circle, obviously, nor is it just a semicircle, because there are little pieces here and here as well. So it's not only half a circle here, but also this little piece here and this little piece here, like from 0 to pi over 6, from 5 pi over 6 to pi, that adds up another like 1/3 of a circle, or sorry, 1/6 of a circle there, from here and here. And so when you take your area here, like the area of the whole circle, pi r squared, that whole area would be 9 pi. What we end up with in this problem is 2/3 of that circle. 2/3 of that 9 pi, and that's a geometry statement there. We're seeing 2/3 of that circle. It's basically going from 0 to pi over 6, so that's like 1/12 of a circle. This is another 1/12 of a circle, and this is half of a circle. So you add up all those pieces, you got 2/3 of a circle. And that circle, the whole circle has an area of 9 pi, and so 6 pi is that extra piece there. So you have to add that 6 pi to the calculus area you get looking from pi over 6 to 5 pi over 6. That gives you that as a total area. Part B now says, now think of this as a particle moving along that polar curve. And then they tell you that theta equals t squared, which we'll need that to make a substitution later. We want to find the time t that makes the x-coordinate of the position -1. So let's go back and think big idea. X-coordinate is going to be r times cosine of theta. All right, we're given r, so here's your r times cosine of theta. That's your x-coordinate for your position. Now, they said to put this in terms of t, and that theta equals t squared. So that's why you're seeing that substitution made there. So here's an expression for x of t, the x-coordinate of the position when theta equals t squared. And we're supposed to figure out, where does that expression equal -1? Make your calculator do that. Graph that expression, graph -1, find the intersections, you'll get 1.428 as the solution there. And then in part C, they want you to find the position vector for that particle. I've actually already found the x-coordinate of the position vector. That's your r cosine theta there. And then in terms of t as well, then your y-coordinate is r sine theta. So here's r times sine of theta. Plug in t squared for theta. Why am I plugging in t squared for theta? Because they told me that they were the same, and they want this expression to be in terms of t. And then, let's see, we're supposed to find the velocity vector after that. Well, if we know the x and the y's, then we just need the derivative of each of those at 1.5. Do math 8, make the calculator do that. Take the derivative of this when t equals 1.5. Take the derivative of this when t equals 1.5, and you'll get your two components of your velocity vector, your x and your y. All right, so that's the 2013 problem. And then a Form B problem to finish it up here. I don't have the average for the Form B problem, but I would expect it to be a pretty low one because there's a lot of things happening in this problem that's a little bit different. First of all, we have to find our own bound here. They give us this graph of a polar curve, 1 minus 2 cosine theta. But now they just give you this little bitty shaded region to find the area of, or at least write an expression for the area of this thing. And we don't have the bounds for this curve. We have to figure out, you'll notice on this curve doesn't start over here. It starts at -1 and then kind of curls around until the r ends up being 0, or right there at the pole. We have to figure out that end time where we're at the pole. Clearly, this is from the beginning of the curve all the way until this curve hits the pole. So we have to figure out, where does this expression, where is this 1 minus 2 cosine theta equal 0? And if you do a little bit of moving things around, you're going to find pi over 3 as the solution there. It's the place where cosine of theta is 1/2. So the reason they wanted you to find your own bound there is because it's a pretty basic unit circle thing. And once you find that bound, now it's 1/2 the integral of r squared d theta. If you couldn't find that bound, notice, if you just set this up correctly, even if your bounds are wrong, they call the bounds the limits here, you can get a point for the integrand. If you've got the 1/2 r squared d theta, really if you've even got the r squared d theta, because they're putting the 1/2 out with a constant, you can get one of these points. So don't get thrown off and say, well, I'll never find that coordinate there, so forget it, I'm just going to skip it. Make sure you write it out, make up a bound there if you have to, because the setup could get you worth 1 point if you understand, if you kind of demonstrate that you know how to find the area of a polar curve. Now, their solutions for part B and part C, I think B is confusing, and I think C skips all the good parts. So what I've done is I've written this out myself, and I'll kind of try to talk you through it, and said I'm going to come back behind the camera here and hopefully zoom it to where this is easy to see and focused properly. So, part B wants us to figure out, let's see, an expression for dx d theta and another expression for dy d theta. So I can flatten this out as much as possible here. So we know to find dx d theta, we need x. Well, x is going to be r times cosine of theta. I have to move up a little bit so you can see it a little better. There, here. The r is given to us. X is going to be r times cosine theta, and that's what I've done in that second step there. So now I can take the derivative of that expression just using the product rule, not doing all the crazy kind of stuff they did in their solution. I just took that 1 minus 2 cosine theta times cosine theta, took the derivative of that with respect to theta using the product rule. And that's what you see here, which, by the way, is totally fine to leave this way. You could box this in and be done. I just wanted to show you the algebra steps that would get you to the exact same answer that they had on the scoring guide. But you can leave it like this, and that would be fine. Same for y. Y is r sine theta. So now dy d theta, we're going to do a product rule thing again there. You can kind of check that out again. As soon as you get that dy d theta expression, that first expression, you can leave it that way. All they did there was 2 sine theta times sine theta to get 2 sine squared. So you can see that my answer looks the same as theirs. Instead, I was going to box these in just to show you that I got the same thing that they got on the scoring guide. But this is fine for your answer if you want to leave it. This is fine for your answer if you want to leave it. That's your dx d theta and your dy d theta in part B. Oh. And then in part C, I figured you'd want to see where all those numbers came from. Oh, we're writing the equation of a tangent line, so we need dy dx. First, I went ahead and found the x-coordinate and the y-coordinate. Just plugged in pi over 2 in for theta. X is 0, y is 1, if you work that out. So I already know most of my tangent line equation is going to be y minus 1 equals the slope times the quantity x minus 0. I have to figure out what that slope is, so I'm looking for dy dx. And now, so we're going to come down some here, and you can see dy dx is going to be dy d theta over dx d theta. Let me see if I can get this set a little bit better for you. There we go. Dy d theta over dx d theta gives you dy dx. I actually have dy d theta and dx d theta already from part B. Now I can just plug in pi over 2. So dy d theta, you can see some unit circle things happening there. This actually was a non-calculator problem on this Form B, but that's very, very rare that you would see that happen. So they actually had to get all the way to the fact that dy d theta equals 2 with all your trig there. Similarly, dx d theta, plug in pi over 2 everywhere, comes out to be negative 1. You see that there. That makes dy dx, dy d theta over dx d theta, so 2 over negative 1 is negative 2. That's the slope of my tangent line. And so I plug that in there for dy dx, and there's my tangent line equation. Y minus 1 equals negative 2 times the quantity x minus 0. So that kind of finishes that up, and hopefully that makes a little more sense to you. And if not, we'll figure it out on the next time we're together in class.